use the pi model this time to configure the equivalent circuit to this common emitter circuit as shown, and then find the voltage gain. So the objective is to find what is the voltage gain in AC for this circuit. Okay? So the voltage gain, if you look at the circuit, you have an input voltage and you will have an output voltage. Let's call it from here to here, call it V out. And AV, which is the amplification of voltage, will be equal to V out over Vin. So looking at it from a top view, it will be this voltage against this one. So the ratio will give you AV, or the amplification factor. V out being bigger than V in, for example, will give you an AV greater than 1. If they're the same, then the AV is 1. Now, for a common emitter, that will be usually higher than 1. So now, how do we go and find out what is AV based on these components that are in the circuit, including any component, internal components from the transistor itself, based on the pi model? So we're going to use the pi model that we've seen in a previous video. So let's draw the equivalent circuit with the pi model in place. So in AC, we're going to have a circuit with Vn right here. So we'll start from here, vis-a-vis some reference. And we know that R2 and R1 are going to be in parallel to ground. So R1, R2, and this is still the base, this whole line right here, since this capacitor is shorted, right? So what happens? Well, we also have an input impedance, since this is the pi model, called beta Re prime. Okay? On the collector side, what we have is the current generator here called beta IB. Knowing that IB, this is the current IB going into the transistor. Okay? And what else? Well, we also have RC in parallel with it, and RL in parallel with it. So what is V out? Well, V out is against RL. So V out will be from here to here. Right? Good. So what can we do here? How can we figure out what is AV? Well, there are a few things. We can look at V out itself right here. And V out itself will be equal to this current, right? And let's call it IC, right? And since this is the collector, IC times RC in parallel with RL, right? So because the total current going through these two resistors, if they're equivalent as one, times IC will be V out on this end. Excellent. How about Vn? Let's look at Vn. Well, Vn, if you look at Vn, it's really VB, voltage from here to here, from ground to the base. Well, what is that? That is IB times beta times little re prime. Okay. Can we work this together to figure out what AV is? Okay, so let's go ahead and put IC in the numerator times RC in parallel with RL. Let's put the other value in the denominator, and times beta Re prime, right? And what is that equal to? Well, that's beta IB, right? So that's IC right here. This is IC. right? And times RC in parallel with RL, everything divided by IB times beta times little RE prime. Well, we can get rid of beta. We can get rid of IB. So what are we left with? AV will be equal to RC in parallel with RL divided by RE prime. Now, there were a few things we could do to figure out RE prime. Okay, you can go to the data sheet of the transistor, and so you could do this. RE prime equals HIE, and again, we know this is from the small signal section in the data sheet, divided by HFE. Now, here's another trick. There is an ideal value for RE prime, and that would be 25 millivolts divided by the IE, the DC version, or for the quiescent point. So you're going to have to go back to the circuit, figure out what is IE in here, and then you're going to take 25 millivolt and divide it by that value. That means while this transistor is operating, what is the IE in DC, right, based on the quiescent point or the operating point that we have based on specific values you have in this circuit. So you could do it this way, or you could do it this way. But in the end, we can see that we obtain an AV based on specific values from the circuit and an internal value from the transistor as well.